Assalamu alaikum. Welcome to the new lecture. In this lecture, we'll be discussing about the new topic that is the thyristor switch capacitor, and we'll be discussing that uh, why do we don't have the thyristor controlled capacitor. The circuit below shows a thyristor, a capacitor, which is connected in series with the bidirectional thyristor switch. It is supplied from an ideal voltage source with zero resistance and reactance present in the circuit. Now we'll analyze the current transients of the circuit after closing this switch, and this analysis will bring two cases. One case is that when these switches are closed in such a way so that the input voltage is not equal to the capacitor voltage. So when that is the case, when capacitor voltage is not equal to the input or supply voltage and the thyristors are fired, immediately after closing the switch, a current of infinite magnitude flows and charges the capacitor to supply voltage. So in this case, the supply voltage will try to charge the capacitor to the supply voltage instantaneously, and by doing so, it will draw an infinite current, and that too in the infinite short time. It is because since the circuit does not contain any resistance, the time constant for this to happen, that is RC, since R is 0, it will be 0. So it will draw infinite current. The switch realized by the thyristor cannot withstand this stress and would fail. So in this case, since the current is infinite, very large amount of current will flow. So it is possible that in the circuit, any equipment can damage. And the most weakest part of this are the switches, and switches may fail the first. The second thing is that if the capacitor is charged to the voltage and it is fired at the voltage which is equal to the uh, it is fired at the supply voltage which is equal to the charge voltage of the capacitor. It will also try to do two things, that is, the current will jump immediately to the value of the steady state current. Here also there will be no transient because again RC is 0. Since R is 0, we can say that steady state condition reached in an infinitely short time. It will try to change the current from 0 to a finite current, which is the steady state current, depending upon the voltage and the reactance of the capacitor. uh, the current will be drawn, the steady state current will be drawn. Although the magnitude of that current does not exceed the steady state value, the thyristors have the upper limit of di by dt values, and they can withstand during the firing process. Here di by dt is infinite. The thyristor switch again will fail, and they will be damaged. So you can see it from here. We have the voltage, and this is the VC, and we are uh, firing the or we are giving the pulses to the thyristor exactly at this point, so that the voltage difference between two is 0. So when this happens, you'll see that the current will jump from this point to this point, which is the steady state value of this. di by dt is infinity. So in that case, the thyristor will fail. They will be damaged. So these are the two main reasons that we cannot, because of which we cannot change the capacitance in continuous manner, or we can say we cannot give the pulses at any value between 0 and 90 degrees. So we have to give it at alpha is equal to 0 with respect to peak, or alpha is equal to 90 degree with respect to the origin, and alpha is equal to 180 degree with respect to the origin, or alpha is equal to 90 degree with respect to peak. So before that also we need to have some conditions to be fulfilled. That is, so the capacitor should be first charged to the peak. That is what is the condition for the capacitor to be fired, peak of the input voltage, and then switched at the peak of the voltage, as the steady state current at the peak of the voltage is 0. That means we have to first charge it up to the peak value of the input voltage, and then we have to give the supply, give the firing pulses at this, because you can see at this point the steady state value of the current will be 0. It will not change here from 0 to infinity. There will not be any infinite di by dt. So that is why these are two main reasons which uh, enforces us to have the Thatcher switch capacitor and not the Thatcher control rate. Now we'll come to the advantage of slope in the SVC dynamic characteristics, that is the VI characteristic. Although there is a slight difference between the VI characteristics of static type or dynamic type, but usually here we'll be discussing only the dynamic characteristics. Although the SVC is a controller for voltage regulation, that is for the maintaining the constant voltage at the bus, a finite slope is incorporated in the SVC's dynamic characteristics and provides the following advantage despite a slight deregulation in the bus voltage. So the first one is that the slopes substantially reduce the reactive power rating of the SVC for achieving nearly the same control objectives, preventing the SVC from reaching its reactive power limits too frequently, and it facilitates the sharing of reactive power among multiple compensators operating in parallel. So these are three main advantages of the slope that we provide in the dynamic characteristics. So what does this mean? We'll come to know. But these two points are mainly the slope is usually provided in the dynamic characteristic because of these two reasons. Maybe after that, this may be the you can say added advantage to this. Now usually we have this is the same characters that we have drawn earlier for the FC, uh, that is the fixed capacitor. It has to control reactor. But the only difference is that the x-axis is here reactive power. In that case, we have uh, the ISVC current. That is SVC current. That is ISVC. So the reactive power in ISVC will differ only when we multiply uh, this ISVC by VSVC. We get the reactive power of the compensator. So that reactive power will be of the order of parabolic, because you will see that the reactive power supplied by the SVC will be given by the bus voltage square, that is V square, into the susceptance provided by the SVC, that is V square. Let's say it is BTCR or BSVC. So in that case, since we have a square term, it will be parabolic in nature. And from this point to this point it will be constant, because voltage we are making it in such a way to make the voltage constant. In previous case we have a straight line from here to here, but here it is a parabolic line, but voltage will remain constant for this case. So dynamic characteristics will not have a slope for this case, and it has some slope in this case. That's what it is meant. And by having a slope we mean that we are allowing some voltage from this point to this point. You can see here from point A to B all the way around we have uh, constant voltage equal to V reference, but from here to here we have some voltage change from A dash to B dash. When we allow some voltage change we require less reactive power. So figure shown below illustrates two dynamic characteristics of the SVC. One is OABC, another is OA dash B dash C dash. Characteristics OA dash B dash C dash incorporates a finite slope, that is, this has a finite slope, whereas characteristics OAB C does not have any slope. It does not have any slope. The slope has been deliberately exaggerated to demonstrate its effect. Actually, slope, you can see here, the slope here shown may be greater than as compared to the actual one, just to show the actual effect of the uh, actual advantage of the effect. So assuming that the system load line varies between line 1 and line 2, that is, we can say system 1 and system 2, that is, this is system original system, this is system 1, system 2, system 3, system 4, whose voltage varies like this because of this current or because of the reactive power. The reactive power rating of SVC needed for providing the flat voltage regulation is QC. Now for L1, you can see that the reactive power needed will be QCM for this case, because L1 voltage has to be made equal to the V reference. So when this is the case, that means the reactive power that is demanded by the system will be QCM. Now for L1 it will be QCM, capacitive to the QLM inductive. That means for L2 it has to consume a reactive power of QLM to make this voltage equal to the voltage of V reference. So as determined by the characteristics. That means uh, for a system where the slope is not there, you will see that this when system voltage or system change from L1 to L1, L1 to L2, the reactive power demand changes from QCM capacitive to QLM inductive to make the voltage equal to the V reference. However, if a small deregulation in SVC bus voltage is considered, that is this one, if we accept some slope in there, if we allow some voltage change from A dash to B dash, as demonstrated by the characteristics O A dash B dash C dash, that is this curve, the maximum reactive power rating of the SVC required for performing the voltage control corresponding to the same variation of the system load line will be Q dash CM capacitive to Q dash LM inductive. That means for this case and for this system, you will see that it will operate at this point. That means we need to supply only Q dash CM reactive power, which will be definitely less than QCM reactive power. And for L2, it need to consume a reactive power of Q dash LM. Definitely it will be less than the reactive power consumed by the QLM without slope. So it means this Q dash CM will be less than QCM and Q dash LM will be less than QLM. So thus a much lower SVC reactive power rating and hence a much lower cost is required for nearly same control objective. We have the same control objective. It looks like, since we have assumed the slope to be a little bit larger, but practically the slope is very lower, and having a lower slope, or we can say having incorporated slope in this characteristics, we will have uh, lesser reactive power rating required for the SVC, and definitely by doing so we'll be able to lower the cost of the SVC. So it has been shown that the SVC rating can be reduced to half with a slope of 5% in the VI characteristics. That means if we have a 5% slope in the SVC characteristics, we can reduce the SVC rating to half. The resultant trade-off is 2.5 voltage exertion. The voltage will change from 0 to 2.5%, and we know that the voltage regulation, acceptable voltage regulation, is 5%. That means it is still in the we can say acceptable limits, and the rating is reduced to half. So this is how this can be done. That is how this voltage rating can be reduced. One more advantage is that prevention of frequent operation of reactive power limits. Let us say the same figure also shows that there is no slope in dynamic characteristics. Even a small change in the system load line from a small variation E2 to E1. You can see from E2 to E1, small variation will bring this characteristics to their limits, isn't it? This QLM is the maximum, we can say, production limit, sorry, absorption limit, and this QCM is the production limit of this SVC having zero slope. So when voltage of the system changes from E2 to E1. In the no-load equivalent system voltage as viewed from SVC bus, it may cause the SVC to transfer from one end of the reactive power range to the another and to maintain the voltage constant. So it will drag it to the limits of the rating of this SVC. The reactive power limits of SVC are reached more frequently if the AC system tends to be strong. So they will go to the reactive power limits. The effectiveness of SVC as a voltage control device therefore becomes limited. So its effectiveness will be limited. With the finite slope in the VI characteristics, when we have the finite slope, the SVC continues to operate in the linear controllable range for a much larger variation in the load line and load line of the external AC system. If we incorporate the slope, so you can see E2 and even is it does not belong to the extremes of this characteristics. This E2 will only draw a voltage, sorry, reactive power of QLM dash, or even will supply a reactive power of Q dash CM. So in that case, it will not be dragged to the limits of the VI characteristics or the rating of the SVC. So this is one more advantage of this. So I'll not discuss the third one because that is not more important. That's actually a disadvantage of this. So I want you to uh, just remember it. The third advantage is it facilitates the proper sharing of reactive power among the multiple compensators which are operating in parallel. So this was about the advantage of the slope. Now let us one more thing. For instance, the SVC can exercise voltage control for significantly larger variation, or we can say it will go to the limits of the uh, VI characteristics for a larger voltage variation, that is from E3 to E4. So that is the advantage of this, that it does not go to the uh, extremities of the rating of the SVC. Now we'll discuss about the influence of the SVC on the system voltage, how this system voltage will change by the SVC characteristic or SVC current or SVC susceptance. Let us assume that we don't have any coupler transformer. The SVC behaves like a controlled susceptance. We have a controlled susceptance over here, and its effectiveness in regulating the system voltage is dependent upon the relative strength of connected AC system. So, its effectiveness will be definitely depending upon it is how it regulates the voltage. The system strength or equivalent system impedance as seen by the SVC bus primarily determines the magnitude of voltage variation caused by the change in the SVC reactive current. So SVC reactive current will determine the system voltage by changing the SVC susceptance. This can be understood from the simplex representation of power system and the SVC shown in the below figure. You can see from here we have the system, we have a bus where the SVC is connected, we have the control which actually uh, compares the reference voltage and the actual bus voltage, and as per that requirement you will see BSVC will be changed. In this representation, the effect of the coupling transformer is ignored and SVC is modeled as a variable susceptance at high voltage bus. It is, it is directly connected to the high voltage bus. The SVC is considered absorbing reactive power from the AC system while it is operating in this inductive mode that we know. Now the SVC voltage, bus voltage, that is VSVC, is given by the following equation, that is Vs is equal to ISVC, because the current flowing through here will only be ISVC, into XS, that is this, plus VSVC. So the voltage equation will be like this. Now linearizing the above equation gives the variation of the VSVC as a function of the change in SVC current ISVC. We'll just differentiate it. So the differential will not be close to 0, will only have a delta. So thus for the constant equivalent voltage source Vs, that is this, it will be equal to 0 delta ISVC into XS plus delta VSVC. So delta VSVC will be equal to minus XS delta ISVC. That is what here it is written. Let us say it is equation 1. Now the VSVC is also related to ISVC through the SVC reactance VSVC as follows, that ISVC is equal to BSVC into VSVC, that is this one. This voltage will be equal to ISVC into BSVC. So again, differentiating this with respect to BSVC and this, we can see partial differentiation. We are doing the partial differentiation, first differentiating it with respect to this, and then differentiating it with respect to BSVC. So delta ISVC is equal to BSVC naught. At that time when this is differentiating, we can call it as BSVC naught into delta VSVC, and delta BSVC differentiating this, keeping this constant, it will be VSVC naught, it will be constant there. So substituting delta SVC from this equation into this equation. So here delta VSVC is equal to minus XS multiplied by BSVC naught into delta VSVC plus delta BSVC into VSVC naught. So by rearranging the equation and making this E ECSR, which is nothing but effective short circuit ratio, that is equal to 1 divided by delta VSVC divided by uh, delta ISVC, and XS is equal to 1 by XS is equal to PS. So in that case, the equation will be finally modified like this, that is minus delta VSVC naught divided by ESCR in plus BSVC naught. This will be delta VSVC divided by BSVC. That is the change in this SVC voltage with respect to the change in the susceptance of the BSVC. We'll get this voltage, sorry, this relation, and this relation we can get the value of the change of this V with respect to B. So where ESCR is equal to effective short circuit ratio defined as this. So where BS is the equivalent system this susceptance. So I think this is enough for today. I will stop over here. I will continue in the next class.